Okay, so we're going to talk about Chapter 10. And let me get rid of some of this stuff because it'll make me crazy. So, in the cups that you were holding with the water and the salt in it, something important to note, whether it's in the cup or whether it's what we're going to talk about tonight, we are not talking about, here's what we're not talking about, making or breaking chemical bonds. You didn't pull apart, at least I hope you didn't, any of those water molecules, right? The whites. I don't even know if I could pop this little white off. I don't think I can, right? Okay. Right. But if I did, that would be a chemical bond I was breaking between the oxygen that's red and the hydrogen that's white. All I was doing was either putting them all close together, letting the magnets kind of do their job, keeping them in the cup, or I could take them, and I could spread them out. I could put one here. This is when I start throwing them around the room. Okay? I could spread them out. It's not anything terribly exciting. And what's the difference between those two processes? Well, you should have learned about it. Thank you. In Gen Chem 1, like the first week, chemical versus physical change. Chemical change, you're making or breaking chemical bonds. That would be like if I could pop this hydrogen off of a water, okay? Breaking that chemical bond. You talked a lot about reactions and bond enthalpies and all that in Gen Chem 1. That's not what we're talking about here. All we're talking about in this chapter, physical changes. Physical changes, the most common, the most common being change of phase. Physical change from a solid to a liquid, melting a piece of ice. As boring as that is, that's a physical change. Going from liquid to gas, or vice versa, okay? So we're talking about physical changes. We're not making or breaking bonds. Okay, that's really, really important. And so because of that, it's really important to actually just start with a good understanding of, at the molecular level, what's going on in the different phases. Okay? And again, I'm going to talk about my magnets and all that too in just a second. So let me kind of shrink this. These properties here at the bottom, don't mind. This says table 11.1. Guys, I've been using these slides for many books. We change textbooks all the time. Content doesn't change. So although it says table 11.1, don't go to chapter 11. You won't find table 1. It's an old table. But what it is, this is simply a table of the description, solids versus liquids versus gases, okay? And let's see if I can blow it up probably a little bigger there. I'm going to draw some stuff underneath it. So let's talk about solid versus liquid versus gas. Again, dumb analogy time. All right, so here we go. So we'll start with the solid. And this is true for any solid particle. And that is, you'll see how good of an artist I am here in a second and why I don't have an art degree. Oops. Really fancy, I know, right? Got a degree for that. No, I didn't really. So solids, particles, are really close together. And again, you can read this up in the table. I'm just going to kind of give you a visual of it. I like to think about solid molecules like a military formation of people standing at attention. You guys have all seen on a movie or a TV show a group of folks, men or women, that are in the military, and they're standing at attention, right? What's going on when they're standing at attention? Well, very little, right? They're standing at attention. They're not talking to each other. They're not moving around. They're supposed to be standing still at attention. Okay, so there's that. Very little movement. They're supposed to be, and I wasn't in the military, so I think it's an arm's length. I don't know if anybody who was in the military can tell me, but they're supposed to be equidistant apart, right? I don't have one guy over there standing at attention and one guy over there and over there. They're kind of standing in a nice, tight area, not moving much. But these folks are breathing, thankfully. They're blinking. So there's a little tiny bit of movement going on. Now we're going to compare this to something in a second, and you'll see where I'm going. So closely packed, not moving a lot. Very orderly. dressed the same, right? Everything the same uniform, the same all that. That's my solid. Liquid, you guys are my liquids. I got my container here, right? Got to put us in some kind of container. The container, let's say, is this room. Now, again, now we have something to compare to. Go back to what I just said about the military formation of people. Okay? You guys are not nearly as ordered, especially with the extra desks in here today. That throws me off. Some of you are sitting closer together. Some of you are further apart. You know, you're not moving out of control crazy. We'll get there in a second with my gases. But you're moving more than, again, let's say a group of 20 military men and women, right? You're moving more. You guys are writing, you're moving around, you're not like confined. You're not dressed the same, you're, you know. Okay, so you guys are my liquid. And then I've got my gas. And again, need a container, because they'll go everywhere. Here's the analogy I always use for a gas. We leave the classroom, and we bring in 22-year-olds. I have a niece who's 2, she's enough, and that's 1. Can't imagine, 20, bring in 22-year-olds into this room, shut the door, and we leave, and we stand outside and we watch. What do you think's gonna happen in this room, or any room? 22-year-olds. No adults, no rules, no anything. We just lock the door and let it be. What's gonna happen?
Someone's getting hurt.
Yeah, I like to say it's sheer chaos, right? Imagine these kids, they'd be everywhere, right? They'd be moving a lot. They'd be bouncing off the walls. They'd be bouncing off each other. It would be insanity. They're moving tons and tons and tons, like until they collapse. They would keep moving and moving and moving, bouncing and moving, and sheer chaos. The complete opposite of a military group of men and women standing at attention, right? I can think of nothing more opposite than that, and nothing I would want to be a part of. And as silly as those descriptions are, that's at the molecular level, meaning if I could take a microscope and look at a sample of like ice, of H2O and ice versus liquid versus gas, if I could take a really powerful microscope and look at it, that's exactly what I would see. Total order, solid, all the way through to total chaos, my gases. Now, and even more important, and what we're going to really focus on in this chapter, talking about the transition or transitions between the different states. So remember, physical change does not change what you have. H2O is still H2O. Not making or breaking chemical bonds. We're simply changing physical state, and that means changing the energy, how much they're moving or not moving, changing the distance between them. And so, as simple as this is, you guys, I'm just going to use 2 water molecules as my example here, because I only have 2 hands. Okay? But imagine there's millions and billions of these. Okay? I don't have millions and billions of hands to hold them. So I'm just going to do my example with 2. Here's my solid. Solid are right next to each other. Again, military formation of people would be equidistant apart. Solid, liquid, gas. And then gas, liquid, solid. When we change physical state, the only thing that's happening is we're either increasing the distance and energy, because they're moving a lot more, or pretty still. We're increasing the distances or bringing them back together, depending on, again, solid, liquid, gas. And so you can even, when you play with these things, and I know this isn't hard to do, but to start from, let's say this is my solid, and to go to a liquid, you can physically in your hands feel that you have to put a little bit of energy in to separate them. The magnet isn't super strong in there. It's not ridiculous. I don't need a friend to pull it apart and help me. It could be. But I can definitely feel that I've got to put a little bit of effort in to separate the magnet. And different substances have different quote-unquote magnets. Meaning some I can separate with my hands, it's really easy, just with my fingers even. And some magnets are so strong, I would need help. I have to put that much effort, energy, force, whatever, into it. Okay? So phase change and understanding just the real basics of it, what it is, putting distance between the particles or bringing them back together, and keeping in mind, again, the idea of magnets. The stronger the magnet is, the more energy it's going to take to separate them, going from a solid to liquid, just as a basic example. And that's what we're going to talk about. What are the magnets? What are the forces that hold them together really, really tight and take lots of energy to overcome? Or, for a lot of things, the energy that's so small, because the magnet's so weak, it doesn't take much energy at all to overcome that. That's what we're going to focus on. Okay. All right, and so those forces are called intramolecular forces. Intermolecular. Now, before we go any further again, lots of kind of definitions, things to explain. What's the difference between an inter and an intra? Well, it's the same as the difference between an interstate and an intrastate. Inter is between different molecules. Just like an interstate goes between Illinois and Wisconsin, for instance. Intramolecular, sorry, it's got like a glare right on that middle of that. Let's see if I can fix that. There's not really a glare there. Oh, hang on. Let's see if I turn that off. There, it's better. Intramolecular, that's the chemical bonds. That's what holds the hydrogen and the oxygen together. So this is a bond, and then these are my, what I was calling magnets. The force is holding between the molecules. Just to give you an idea of energy differences, you don't have to, the numbers aren't going to mean a whole lot other than we're going to compare the two. And it should be a pretty simple idea. So the amount of energy it takes to vaporize 1 mole of water. So 1 mole of water has a mass of 18 grams. It's 18 milliliters, so, it's, I don't know, it's not that much, right? 18 milliliters, not much. It takes 41 kilojoules of energy to take that from a liquid to a gas. And you say, okay, well, big deal. Well, yeah, for what we're talking about right now, that doesn't mean much until we read the next line. Compare 41 to 930. 930 kilojoules of energy is what it takes to break the chemical bonds in that same amount of water. Okay? So, moral of the story, these forces, these magnets, are not nearly as strong as an actual chemical bond. But that's a substantial amount of energy, 41 kilojoules, and we have to account for it. So in what we're leading up to tonight, when we talk about and calculate the energy needed to change phase for different substances, changing physical state, like vaporizing something, that will play a part in it. We'll get to that in a second. So a substantial amount of energy, but not nearly as much as how much it takes to break a chemical bond. And I always do this. This is kind of my example, you guys. And maybe this will keep it fresh in your mind, the difference. So again, vaporize 1 mole of water. I can separate my molecules with my hand. Okay? One hand, even just a couple of fingers, I can separate the molecules. The magnets aren't that strong. Breaking a chemical bond, that would be like snapping this pencil. I need to use both my hands, and I got to put a lot of force into it. That was breaking a chemical bond. This was simply putting distance between the particles. Okay? And I sacrificed a pencil. Yeah. I know, I'm not going to tell anybody. Okay. Some things we're going to look at. So why do we care? How do we know about these intermolecular forces? Well, if you can see here in the bottom right, this is the reason that different substances have these different properties. Why does water boil, for instance, at 100 degrees Celsius, whereas methane, that's the gas that comes in our lab, in our Bunsen burners, I want to say it's like 20 degrees Celsius. It's really low. Might be lower than that. Drastically different boiling points, yet CH4 and H2O are very similar in size, very similar in weight. What's the difference? Well, it's what we're going to learn about these intermolecular forces. Melting point, these other things again, sorry, I got a little, there we go, that's a little better. Delta H vape means the heat of vaporization. That's simply the energy needed to vaporize. Heat of fusion, that's the next one. FUS is fusion. That's how much energy it takes to melt, solid to liquid melt. We use the fancy word fusion. And then anybody want to guess what the last one is? SUB? What's that? Sublimation. What's sublimation? You guys remember what sublimation is?
From solid to gas.
Exactly. It goes directly from solid to gas. So these last three, again, these are just energies associated with changing physical state. Okay? So we're going to look at all those and how they're related to these fancy things called intermolecular forces. Okay, I can't do this on my iPad. So for those that are watching this on the computer, they're going to miss out. I'm going to keep like a running tally on the board of these forces. And bless you, the reason is we're going to talk about and compare them in a little different order than the book teaches. And that's okay, it doesn't really matter, but. All right, so we're going to start with dipole-dipole. Obviously, that's the first one up here. Here's where I talked about last week. You have to be able to know, recognize if a molecule is polar or not. This is it right here, and this is huge. So if the molecule is polar, that means it has one side of the molecule that's electron rich and one side that's electron deficient. So for instance, in water, if you look at the Lewis structure and then think about the dipole moment, I'll draw it like the shape is bent. Right? You got these lone pairs up here for water. The dipole moment for water is in that direction. And all that means, what that means, is that this side of the molecule up here is electron rich. We might also say it's partially negative. And down here at the bottom where the hydrogens are, all the electron negativity is being pulled away from them. It's electron deficient, or we would say partially positive. And so anytime we have a molecule, I like to think about it as being lopsided, where the electrons are not equally distributed throughout. One side is heavier than the other side with electron density. That makes a polar molecule. And of course, we don't just have one water molecule. We've got millions and billions and trillions of them. I mean, even in your cup, there's like, 10 or 15 of them. And so what do? Well, if you can see up on the slide there, it looks like little Tylenol capsules or something. But they line themselves up so that the positive on one water molecule, where the hydrogens sit, I just erased what I should have probably erased. Where the hydrogens sit, the white, guys, here, the white on the water molecules we just talked about, they line themselves up so the white is next to its neighbor's red. Because there's an attraction there. White and red in our little molecules attracted to each other. And they all line themselves up like that. What else happens, or doesn't happen, there's no attraction between the two whites. Remember we had that on the board, what doesn't attract? If you tried to push these two whites, the hydrogens together, they repel. In fact, you can actually feel, if you try to push them together, you can feel the magnets pushing apart. Like, no, not going to do that. You're not going to make me. And the two reds do the same thing. The partially negatives push each other away. They repel each other. But thankfully, they can all line up in such a way that they maximize those attractive forces. That's what happens. And it doesn't matter if it's a water molecule or anything else that's polar. That's the idea. Polar molecules have a partially positive and a partially negative side, and they all line up to maximize those attractions, just like with our positive and negative sides of the magnet. Okay? And so that's what's called dipole force. And it's going to be I'm going to make it my number 3 force on my accounting up here. the reason it has that name is because, again, polar molecules have a dipole moment. That's it. And that's all you need to know. But now we'll talk about it. The most important, again, is recognize if it's polar or not. All right, I'm going to come back to this guy. This is a unique one, and you'll know why in just a second. I'm going to come back for now. All right, so, and the books all do this, and I don't know why, but when we talk about these three, and when I just talked about them, I was talking about them as pure substances, meaning I had a cup of just H2O. I hadn't thrown salt in, I didn't have anything else, I didn't have nasty RVC water, which who knows what else is in that. I just had that one substance, just H2O, or just CH4, whatever it was up there. But that's not always the case. I can have what we know, again, from Gen Chem, what's in your cup. You can have a mixture. Salt water, probably the most common mixture of all. Salt water is a mixture of salt and water, right? Not a pure substance. It's made up of pure substances. And so this last one I kind of pull out. I talk about it separately, only because you have to have, it is only present when you have a mixture. And not just any mixture either, but you've got to have a polar solvent and an ionic solute. And I'll talk about more in just a second about that. So it has a really, really specific kind of narrow range of what it applies to. Have to have a mixture. It tends to be the strongest, you guys, the strongest of them all. But I like to do it separate for that reason. Okay? It only applies to mixtures. Now, if we have a mixture, for instance, of sodium chloride aqueous in water, it would have all of these things. Okay? It would have them all. But without that sodium chloride thrown in water, water would just have these three. So let's talk about that. All right, so a polar substance. Water, I had it on the board, I just erased it. Water is something, it's matter. So water gets check this box. Okay, it gets dispersion. Water is a polar substance, so it also has dipole-dipole. And water very much fits the bill of hydrogen bonding because of this, right? So water, pure water, all by itself, has all three forces. Throw salt in that water, like what you have in your cups, and you also have this guy here. Because your solvent, the substance present in the greater amount, water is polar. So it has, like if you look on the slide right now, it looks like, again, that green capsule. That's a polar molecule. It has a partially positive side to it, a partially negative side to it. So water, that's what's going on here. These guys here, that's water. And then the ionic solute present in the lesser amount, sodium chloride, sodium iodide, whatever you want to throw in there, magnesium chloride, a substance that separates into a cation and an anion when put into water. Just like you saw with your cups, we said the blue was attracted to the red and the green was attracted to the white, and not vice versa. Because, let's see, the green is a negative. It's attracted to the white hydrogens that are partially positive. And the blue is a positive cation, sodium if we're going to use that, attracted to the red oxygen, which is partially negative. And so salt water, or what's in your cup, would have all four forces present. And to, for instance, boil that would take a lot of energy. It would have a high boiling point. To this, why I skipped it. Okay, here's just another visual. I'm sorry, this has got kind of let me see if I hate that glare it's got. This is just showing what you have in your cups, again, that you're going to have a positive cation and a negative anion. Well, this one just has the positives. Has two different positives, sodium and magnesium, showing you, though, that they're attracted to the partially negative side of water, which is where oxygen is, the red in your cup. And then what happens? Well, I don't just have one water molecule and one, what is sodium iodide, sodium chloride. Again, water is the solute. It's present in the far, far greater quantities in comparison to the solute, salt. And so what happens is that a whole bunch of the water molecules, they surround that cation. Okay? It's not just a 1-to-1 ratio. Okay? A bunch of them, they surround that cation from every angle. And that's why it dissolves. That's why when we look at it, salt disappears in water. It doesn't really disappear, but I'm putting distance between the cation and the anion, and it is mixing with the water. And then the same thing happens with the anion, the chloride or the iodide or whatever the negative anion is. But instead of the oxygens all lining up in that direction, the hydrogens all line up and surround it. I don't think okay, but it's just the opposite. So those are the different forces that we look at. And again, I like to have this little, I kind of keep them like this in my mind. That's why I like to keep my accounting as we go through. All right, we're going to do some. All right, my next one, I'm going to put it number 4 on my list up here on my accounting. It's called dispersion, sometimes known as London dispersion. And this one, you guys, is really, really simple. Everything has dispersion. Everything. And that's simply because all atoms have electrons, even if it's just one electron, like hydrogen. Electrons move around. They're moving around in those orbits, do you remember? Outside the nucleus. And at any given minute, second, an electron may be over here 1 minute, and it may be over here another second. It's constantly moving. And so it's called, what's called a temporary dipole is induced. So if at any given moment more of the electrons are on one side than the other, it creates a very temporary, because then they move again a minute later, a very temporary dipole just within that atom. Since everything has electrons, all you need to remember here, everything has dispersion. Everybody gets something. Everything has dispersion. Now we can go a little and explain on another slide now. Example problems here and further and talk about skipped. Second, let me flip back. Let me just show you this guy here. If we have substances that only have dispersion, and I'll spoil it here, spoiler alert, these 5 on this table 11.2, these 5 molecules are all nonpolar, and even though we haven't finished yet with all of our forces, here's the spoiler, I'm going to tell you the only force present in these 5 molecules, that's dispersion. That's all they have. Okay? Now, if you look over on the right-hand side, though, they have drastically different melting points. Remember, melting is going from a solid to a liquid, putting distance between the molecules, overcoming the magnet, the force holding the molecules together. Why is CH4 so low as compared to Ci4? What's the difference, you guys? Yeah.
More electrons.
More electrons, that's one thing. What else? Molar mass, right. Size, which also then more electrons are going to be present when it's bigger. The larger it is, the stronger it will be. Okay? So if all else is the same, and we're going to do some where we compare, they have different forces, but with this sample set of 5, these are all nonpolar, so they do not have dipole-dipole. They only have dispersion, but yet they still have drastically different melting points and would have very different boiling points. Then you look at size, okay? It talks about electrons and all that stuff. The one to where we were. All right. Number 2, I haven't forgotten the one. We're going to go back to it. Number 2 is what's called the hydrogen bond. Probably not a big shocker. Guess what has to be present? Hydrogen. Yeah, shocker there, right? But you have to be careful. It's not just hydrogen in any molecule. It's hydrogen in a very specific bond. Hydrogen with nitrogen, oxygen with hydrogen, or fluorine with hydrogen. Okay? Why? Now, why is that? Well, first, that's a polar bond. It has a very large electronegativity difference between these two atoms, hydrogen having a relatively low, and nitrogen, oxygen, fluorine having a relatively high. So it still fits the dipole-dipole, but it's kind of a dipole-dipole on steroids. So, and I know I still have one left. So my order in terms of strength, the one I still haven't talked about, and you'll understand in just a second here why I didn't. Hydrogen bonding, though, is the strongest of these 3 that we've talked about. We know where the word hydrogen comes from. It's part of this. The word bond, why do they call it a hydrogen bond? It's not actually a chemical bond. It's an attraction. It's a magnet. It's my strongest magnet of the ones we've looked at. The reason that we call it hydrogen bond or bonding is because the only thing stronger in a pure substance is a chemical bond. Okay? The only thing stronger. About the rest of the stuff, guys, if I didn't focus on it, it's because it wasn't all that important. I did want to show you this. You guys can see this. Whoops. These are a couple different examples. Hydrogen bonding, well, they also have dipole, dipole, and dispersion, because they're all polar molecules, and they're all something. They're all matter. And I've got a couple of different things happening. This first one on the upper left, this is just how water molecules will line themselves up next to each other. Again, we talked about the dipole moment. The oxygen of one molecule is going to position itself next to the hydrogen of its neighbor, because that's where the attraction is going to be. And then we can also look at a sample of ammonia right here. Ammonia is NH3. And again, the partially negative side, or the dipole moment, is up in this direction by nitrogen. So the electron-rich area is up here by nitrogen. The electron-deficient is down by hydrogen. So again, you can see that the 2 molecules line themselves up in that same way. And then we can also look at a mixture of ammonia in water. Notice again, it lines itself up. Partially positive side of the NH3 is next to the partially negative side of the H2O. So it doesn't matter if you have 2 of the same thing or 2 different. If they're polar, they're going to line themselves up positive to negative. And I have just different examples down here, a couple different other examples. Again, there's ammonia and water, but now it's, okay, what's the nitrogen going to be attracted to? Well, the nitrogen's going to be attracted to the hydrogen on the water, on the neighboring water molecule. And then here's some other examples. HF, which is polar, has hydrogen bonding as well. It would line itself up based on the dipole moment of NH3. And then you could also talk about it this way. Okay. Let me see if I want to do back and talk. That's kind of some of the same stuff. Let me talked about hydrogen bonding. And again, why is it so special? So as chemists, one of the things people many years ago, they studied the properties of all different substances, and they tracked the properties of all different substances. And this is a chart that shows these are boiling points of different substances. And if we start over here on the right, and you look at the periodic table, you can kind of see where, where's my laser? you can kind of see where these elements are. Their main element, and then it's got a bunch of hydrogens with it, or in some cases just one. And you can see this on the far right-hand side, the Te, the Sb, the Sn. Do I have anything else? Oh, and the I. Those guys are way down here in that fifth row of the periodic table, n equals 5. It's way down here, the bottom, okay? And then as we go from right to left, you can see here's my next group of elements, Se, Br, As. Do I have a Ge in there too? And so as I'm going down from right to left, the boiling point's getting lower. The size is getting smaller because I'm going up the periodic table from n equals 5 to n equals 4. This group right here with S, sulfur, chlorine, phosphorus, silicon, that's my n equals 3 line of the periodic table. So I'm getting smaller and smaller. The atoms are getting fewer electrons, smaller in size. And what happens, as it says right here, my boiling points are decreasing. And there was a regular trend to that. Whether it was, using hydrogens, whatever it was, they saw this trend continually. However, then they got to this group right here. And they saw that there was this huge shift up for NH3, HF, and H2O. But yet, CH4 kind of continued on its way in the direction we would expect. And they're going, okay, what is going on? Why is it then when I get to n equals 2 on the periodic table, the second row, where carbon and nitrogen and oxygen sit, why is it that, first of all, 3 of them shoot way up, come out of the trend or the path that we would have expected, and then why did 1 of them stay on track? And so they started looking at the individual differences between molecules. They started to not only look at this set of whatever this is, 16 different substances, but other substances. And they found the trend that when a molecule had one of these bonds, it threw everything off. It was much higher boiling point or much higher melting point. The properties were quite skewed. And it was every single time it was a polar molecule that had one of these bonds. And so that's why the scientists were able to determine long ago that this is a class of itself. Okay? Because of just this data right here. And yet CH4, when it's just carbon with hydrogen, it's not in that group. Well, a carbon-hydrogen bond, if you remember from Gen Chem, carbon-hydrogen bond is non-polar. Okay? So that's where CH4 only has dispersion. CH4 only has dispersion. It's a non-polar molecule. It doesn't meet the hydrogen bonding. It's not a mixture when we're just talking about CH4. And so that's why there's a drastic difference if we just look at this group over here on the left, why there's such a big difference between 3 out of the 4. 3 out of the 4 have hydrogen bonding, dipole, dipole, and dispersion. And CH4 only has dispersion. All right, so here's how our problems are going to work in class. Whoops, I don't know why that's crooked here. We're going to do one together, and then I'll have one for you to do, and I'll give you a minute or two, and then you can look at your answers, okay? All right, so let's do this one together. For these 4, what do they have? Which ones? These are, now let me preface this, these are pure samples, pure substances, no mixtures of anything. So number 1 is off the table, okay? I'm not mixing them with anything. It's just HBr or Cl2 or I2 or NH3. So help me out, guys. HBr. Let's start with, does it get dispersion? Yes or no? To dispersion? Oh yeah, that was a big yes. How about let's do it. I'm going to make this little table here. Dispersion, dipole, dipole, and then we'll do H bonding. And we'll just I'm just going to make a table to kind of make this go a little easier. All right, so HBr gets dispersion. Let's check that box. And hey, guess what? Let's just do dispersion. Let's talk about dispersion for all of them real quick. Do they all have dispersion? Yeah. Yes. So let's check that box. 1, 2, 3. They're all something. They're all matter. They're all atoms and elements. Give them something. They get dispersion. All right. Dipole, dipole. So the question is HBr polar?
Yes.
You betcha. How about Cl2? Is Cl2 polar?
No.
Nope. How about I2? Nope.
No.
How about NH3? Check that box. Okay? So none, none. All right. Last but not least, you guys tell me of the four. I'll give you a hint. Only one has hydrogen bonding. Which one has hydrogen bonding? NH3. Again, just because it has hydrogen, HBr has hydrogen, it doesn't mean it has hydrogen bonding. You have to be careful and make sure it's an NH, an OH, or an FH. Okay? Okay. Now, the question didn't ask this. The next one, I think the one I give you does. So let's do it for practice. Let's guess, and probably with good accuracy, the order of their melting or boiling points. So, which one is the strongest? Which one's going to need the most energy to separate the magnets, let's say? Which one is the strongest? Okay. Who's next? What do you think? HBr, and why? That's right, but why? It's got the two. Yep, it's got, where are we? It's got, what do we say? The first one had all three. The second one, the HBr, has the two. Okay, now that leaves Cl2 and I2, which we've said accurately, these two only have dispersion. So what did I say about dispersion? Who's next on the list? Who's stronger? I2, and then Cl2. So of the four, and I may be off a little bit, I'll explain why in just a second, but just based on the forces and then our rule for size down here, we could predict their order. Now, I actually pulled some numbers to show you guys, just to give you an idea. The energies associated with these different forces, and you're going to see it's a range, which is interesting. I'll talk about that in a second. 35 to 400. This is all kilojoules per mole. Hydrogen bonding is 10 to 40. Dipole is 5 to 30. And then dispersion is less than 40. Sometimes less than 1 even. So there's a range. Why is there a range? Well, we already talked about just dispersion. The difference between the sizes of those two make a difference with their energy. I like to think for that one, I think about like, a big, huge, heavy molecule takes more energy to get it up and moving and put distance between. It's like rolling a really big ball versus a little tiny ball, pushing a big ball versus a little ball. But the same can be said. We've got different things going on here. I've got different dipole moments. Some molecules have a really strong dipole moment, and some it's relatively weak. But what you have to also remember is if you have a substance that, for instance, has all three, it adds up. So on average, you can just put them in order based on those forces, like we just did. It may not jive exactly, but the questions usually are pretty good of, just based on what you know about forces, what would you predict?
Excuse me.
Mm-hmm.
I didn't understand what made the difference for the weakest and the strongest between the ammonia, hydrogen, iodide, and chlorine.
It's these forces here that we just talked about. The more forces, the stronger they are.
Or the more forces, the stronger.
Mm-hmm, mm-hmm.
Okay.
Yep. All right. You guys, this is your first question. So the same idea applies. Put them in order and tell me what intermolecular force they each have, or intermolecular forces. You can make a little chart table if you want to, like I just did, whatever you want to do. I'm going to give you 5 minutes for that, and you guys, it's a good time for a break, so let's take this to 7:15. Okay, 7:15, and I'll start moving a little faster here because I'm probably a little behind. Let's see if I can get my... You guys, can you write these down real quick if you don't have them in your notes already? I'm gonna try and do some tech support while we're on break here, so. I'll give you a minute to write these, 4 down, and then I'm gonna take this off for a second. Okay, so let's just real quickly talk about some of the properties. Not only melting and boiling, okay, melting and boiling, changing phase of any type is, again, putting distance between or reducing the distance. But there's some other properties that are affected by these forces as well. Surface tension is one, and so some of these I'm going to go through quickly. We're not really going to do much with it. Surface tension, strong intermolecular forces, kind of like with melting point, strong intermolecular forces, high melting point, boiling point, high surface tension. So for this one, my best example, you guys have all seen mosquitoes or flies that walk on the surface of water in the summer. That's what's going on. Water has a very high surface tension. The molecules are being held together very tightly, and I like to think that the little mosquitoes and their little feet can walk across the surface. You can float things, other things like a coin. You can float a coin on the surface of water because water has a high surface tension. If you take something that doesn't, it would fall through. The attraction, again, holding those molecules together, not only does it work with melting point, boiling point, but surface tension as well. Cohesion and adhesion. Again, not going to do much with this, just going to kind of give you the definition. On the left-hand side, what this is supposed to see, what you're supposed to see, this is a beaker with water in it, and a test tube has been put inside of it. And so we're talking about water molecules and glass molecules. And as we know, water will go inside of a test tube like this, or even if you want to think about putting water in your graduated cylinder. The water sticks to the sides, but yet water and glass are different. They're unlike each other. But that's what's called adhesion. And what's actually happening, you know that thing we call the meniscus in the grad cylinder that forms this little guy right here? That's because the molecules, I like to think, the water molecules, they're trying to get away from the water. They really don't. They're not attracted to the sides, so they're kind of huddling up together, and that forms this little inverted bubble there. No, glass and water are not. They're unlike molecules. That's called adhesion.
What's going on?
Well, you have a solid and a liquid. You're forcing it. I mean, if they had a choice, they wouldn't be together.
Oh, yeah, sorry.
Okay. Cohesion, now you've got like molecules. And what's going on here, this is a test tube with, for instance, liquid mercury, something we don't really mess with anymore. It's too dangerous. And glass. So those molecules are much more alike. They have dispersion forces. And again, what I want you to notice the difference, look at this. It's the opposite of the meniscus that we're used to, that underneath the U comes the other direction. And I like to think because these molecules would be gladly connected to, they're attracted to the glass. So they're trying to actually reach out and grab it. All right, just some definitions. I'm not going to worry about it. Here's one more. Viscosity. I know when I think about viscosity, I think about motor oil. You hear commercials, they talk about, the viscosity of Pennzoil or whatever it is, different motor oils. We can talk about viscosity for any liquid, though. It's the measurement of a fluid's resistance to flow. So if you've ever played in your kitchen with, for instance, corn syrup, it's really thick, it's sticky, it's very viscous, it pours really slow. Syrup, like pancake syrup, that also is fairly viscous as well. This is another force. Again, the stronger the molecular forces, so the opposite here, the stronger it goes, the higher the viscosity. Kind of a side note, water. Water is this crazy, crazy thing that, and for very good reason, especially this time of the year, water, liquid water versus ice. The maximum density of H2O is actually at 4 degrees Celsius. What does that mean? Well, first of all, at 4 degrees Celsius, H2O is what phase? Liquid or solid? At 4. it's liquid. And maximum density, what that means, density, more molecules, or the molecules are closer together. So at 4 degrees Celsius, when it's actually a liquid, the molecules are as close as they're going to get, which is kind of opposite of what we've been saying. I said, I talked about putting distance between particles, and as substances go from a gas to a liquid to a solid, they get closer together. And that is, if you look at this little graph here, that's generally true, right? As I'm cooling it off, heading towards the solid phase, the density is getting greater and greater. They're getting closer and closer together. But then it does this like weird crazy thing right here in that little range, and that's unique just for water. Now, what's going on? Well, in terms of density, at 4 degrees Celsius, again, that's when the molecules are closest together. They're maximizing the space, the distances between them. It's just something water does. We don't really know why it's at that particular temperature. But here's the cool and good thing. If it didn't, ice cubes would not float in your cup. I have ice cubes and some fruit and stuff in here. I have ice cubes floating up here at the top. You guys think about a drink? Ice cubes float at the top, don't they? They're actually lower in density than the liquid. Crazy. And you go, okay, well, so big deal, right? Well, okay, big deal, but here's where it is a big deal. Right now, I think even the Rock River is probably totally frozen over, or primarily frozen over. There's ice fishermen that they drill down, and there's still fish swimming around in the water underneath the ice. If it was the reverse, if ice had a higher density than water, bodies of water would freeze from the bottom up. And imagine what would happen if bodies of water froze from the bottom up. They'd push all the fish out. So it's kind of a good thing. It's a very good thing. Interesting, though. Just a little side note. All right, we've talked about phase changes already, sublimation, melting. I just assume most people know the terms, melting, freezing, vaporizing, condensing. The ones that we don't use much, we talked about sublimation earlier. Dry ice does that. Around Halloween, we have lots of that happening. People use that a lot for effects and things. Deposition is the opposite of sublimation. Instead of going directly from a solid to a gas, it's going from a gas to a solid. All right, some more things here. I'm not worried about this. I'm going to skip past this. All right, another property, and one we're going to focus on here for a little bit. And in fact, we're going to do our lab on Thursday over this. Vapor pressure. So if I brought a cup of water in here, like imagine this really was water in this little cup here, and I set the cup here, what would happen after a couple days, after a couple of weeks? What would happen to the water in the cup? It would evaporate, right? So it's pulling energy from the surroundings, from the desk, from the air. Molecules are warming up. They're getting energy. It's a really slow process if I'm not putting it on a hot plate or anything, But eventually those molecules will get enough energy and they will jump out of the liquid and become gases and go floating all around, and they'll be gone. And yeah, a cup of water, if you leave it out, will evaporate over some time. The warmer it is in the room, the quicker it goes, but it will evaporate. Well, what's this? Vapor pressure is when you have a liquid like this, and you put a lid on it, and you seal it. So the gas can't escape. Okay? And what would happen over time, what happens depending on the liquid, which we'll talk about, some quicker than others, pressure builds up inside that container. You've got gas molecules moving all around, and the more gas that's produced that evaporates inside the sealed container, the greater the pressure. Because when we talk about pressures, we talk about gases. Now, if I put water in here and put this lid on it, what would happen? It wouldn't evaporate. It would a little bit, but then it would condense back down. And would pressure build up? When I took the lid off, would I hear that gas? No, I wouldn't hear that, okay? Because water has a pretty high list of intermolecular forces, strong ones. But if I take something like acetone, acetone is what fingernail polish remover is. I do this all the time. I used to. I would forget to tighten the cap on the fingernail polish remover, and next time I'd go to grab my bottle of fingernail polish remover, it would be empty. Acetone, unlike water, acetone has just the weak forces. Acetone is also what we call a volatile substance. Volatile substances evaporate fairly easily. A lot of times they're flammable too, so you gotta be careful. We're gonna deal with an alcohol, I think it's ethanol, on Thursday that does the same thing. When you put it in a sealed container, especially, it'll evaporate quicker than water, for instance. It doesn't have quite as high of the forces. So equilibrium, that's our first time you're hearing this word, equilibrium vapor pressure is that pressure I was just talking about when this dynamic equilibrium exists between the two changes in phase. Condensation, liquid to gas, or gas to liquid, and evaporation, vaporization, liquid to gas. So in a sealed container, what that means is you've got the liquid that's evaporating, but then the gas that's condensing. And they reach a state, what's called equilibrium. You'll grow to hate that word over the next few months. They reach that state right here where the rate, because what equilibrium actually means, equilibrium means the rate or the speed of the two processes is equal. That's what it means. And so what would that mean in terms of, like us looking at a container with a liquid that has a lid on it? We would not see any difference in the amount of liquid. Versus take the lid off, it'll all go eventually, some quicker than others. So again, this is just another property that's affected by these different forces we're going to look at here in just a second. So this kind of gives you a little bit of an idea. On the left-hand side, sorry, again, the glare's kind of bad. On the left-hand side, you've got just your initial frozen liquid. So it's got some solid liquid emptied out, so it's a vacuum of space inside. And then it has, you can't really see it in the overhead, it has this, we call it a side arm, that has liquid mercury in it. And we start it, like we hit the stopwatch or close it up or put it in there, whatever. And originally, these two are the same because it's empty. And then after however much, sometimes this happens in 5 seconds, sometimes it takes 5 days. But once it reaches that equilibrium where the rate of condensation is equal to the rate being the key word, of evaporation, when those are the same, what happens, you can see now I have all these gas molecules in what had been a vacuum of space, empty space. And those gas, the more gas you have, the greater the pressure. And now you can see over here on this side arm that these two levels of the liquid mercury are not the same, because I have a gas pushing down on that liquid mercury. They're trying to get out. They're trying to get the liquid mercury out so they can escape. But that builds up a pressure, okay? And it's related to these forces and things we're going to talk about. So that leads us to our very first equation of the chapter, and one more definition here, the heat of vaporization. We talked about that. It was on one of my first slides. It looks like this, delta H vape. So the amount of energy it takes to vaporize 1 mole of a substance at its boiling point. So not only we're going to learn, does it take energy to change the temperature of something? You learned about that in Gen Chem 1. But it also takes energy to change phase, because when we change phase, we're having to overcome these forces. And so this isn't quite the equation yet we're going to use. I'm going to explain this. And this is when I give my big warning, especially if you take Dr. Check or if you had Dr. Brinkley. I hate deriving equations. I just hated it in math. And so I'm just going to show you the equation we have to use, and I'm going to give you that equation on the exam, and I'll show you how to use it. Okay? So this is what's called the Clausius-Clapeyron equation, and basically it was this scientist who studied, again, these properties. He comes back into play next chapter with some other stuff too. But he was interested in pressures and temperatures and these different substances. And so what he first did was just tried to graph the different vapor pressures versus temperature for different substances. And he kind of saw these funky curves. And well, that's not all that useful when we're trying to look for relationships. When we want to look for relationships, what works best is when we have a straight line, a linear relationship. And he found if, let me blow this up, if he took the natural log of pressure, the vapor pressure, and plotted it versus 1 over the temperature, and this should be in Kelvin, that he did get a linear relationship. And therefore, when we have a linear relationship, we can write it as, everybody knows the big famous equation, y equals mx plus b, right? That's our equation for the line. And that's where this original equation comes from. Again, this isn't quite the form we're going to use in yet. P, again, is that vapor pressure we were just talking about. Temperature needs to be in Kelvin. We're dealing with gases, so remember back to Gen Chem 1, you always put temperature in Kelvin. And then R is our gas constant. Again, same gas constant that you used in PV equals nRT. And then C is a constant as well that, in fact, in a second here I'm going to show you we don't actually use, because what we really like to do is comparisons. So for instance, if I change the temperature, how will the vapor pressure change? That's what type of thing we're going to be looking at. If I change temperature, so you see I've got T1s and T2s here. If I change temperature, how is the pressure going to change? And remember, back to Gen Chem 1, pressure and temperature are related. Remember, you had your equation P1 over T1 equals P2 over T2. Now, why are we not just going to use that equation? That seems so much easier than this convoluted thing up here. Well, that's because what we're talking about here is changing phase. We're talking about vaporizing and how the pressure changes when we're talking about different temperatures, or do it at different pressures, I'm going to get different temperatures at which it vaporizes. So it's because we're talking about changing phase versus what you did in Gen Chem 1 with your P1 over T1s equals P2 over T2. That was just a gas. It was a gas at P1 and T1. It was a gas at P2 and T2. This we're talking about vaporizing, hence the heat of vaporization that's right there as well. So we're throwing in the energy factor with it as well. Okay? So I'm going to throw this equation up on the board so that we know how to use it, and then we're going to do it a few times. And hopefully you'll see it's not too bad. I like the bottom one better. You can use either one. I don't remember which one I have on the test. I might have both. I don't know. They work very similar. It's just a matter of whether you're going to throw in the T1 over T2 on top, or which of the two you prefer. Again, I'm going to put in the bottom one. I'm going to write that one up here. As long as you do the math the same, they work the same, I promise. Okay, I promise. All right, so that's what's called the Clausius-Clapeyron equation. And we're going to come back to it in another chapter as well and use it, but this will be your first time seeing it. Okay, so here's an example again. I'm going to work through an example with you, and then I'm going to give you a couple of minutes to try one on your own. All right, so diethyl ether, it's volatile. That's the word I talked about a little bit ago. It means it evaporates easily. If I set a container of it out, it would be gone in a matter of probably a couple of minutes if I just had a little bit. It's volatile, it's highly flammable, organic, it's used as a solvent. Guys, guess what? I could care less if that's what that is. That's great that that's what it is, it explains it, but I'm going to be working a problem where I need some numbers. So when I look at word problems, I like to list what I like to call the givens. What does the problem give me? And I've got them circled up there. I'm going to list them just to kind of really hammer home my point of how to do this. So 401 millimeters mercury, everybody should know that's a unit of pressure. So I'm going to label it P, and for right now just P. And then I see an 18 degrees Celsius. What is that? If it's Celsius, temperature. And then it says calculate its vapor pressure. Okay, so I'm looking for another P at a temperature of 32 degrees Celsius. Does the fact that it's diethyl ether, volatile, highly flammable, or does that mean anything for this problem? No. Okay. And I'm sure you guys have seen this. You've taken Gen Chem 1. Chemists like to be really wordy and give you these crazy long word problems where you need like 4 pieces of information and then the rest of it can just be set aside. So you'll see I say this a lot, like just focus on what's given and, what are you looking for? And see the pretty molecule here? Well, that's really pretty and all, but okay, I don't need that for anything. Okay, I mean, that's what it looks like for those that are interested. But to solve this problem, I could really care less. Now, here's what I've got. Before I kind of jump over to the equation, hopefully you notice there's 2 pressures, there's 2 temperatures. So the only other thing I really want to focus on before I set the problem away is to make sure I pair them correctly. So which pressure and temperature, how are they paired? And then when you read a sentence, they're usually right next to each other. This stuff is at 401 millimeter mercury at 18 degrees Celsius. So I'll call those P1 and T1. And if you called them P2 and T2, perfectly fine. As long as they're paired, that's what matters. They're paired correctly. And therefore, if that's P1 and T1, this must be P2 and T2, right? Now, I'm done. I'm done with this problem in terms of the words and the pretty molecule and all that. Here's my equation up on the board, right? What we just looked at, the Clausius-Clapeyron equation. What am I going to need to be able to solve for P2? Well, I need delta H and I need R. Now, in reality, especially like on a test, you would have been given the heat of vaporization. Okay, they expect us to go look it up. I'm going to have to look it up here in a second. It's a constant for diethyl ether, so I guess that's where it matters what the stuff is. In a problem, normally, I'm going to give it to you. Your next problem that we're going to work in a minute, I give it to you in the problem. And then R, let me write R over here. R is just a constant. You're not going to be given that in the problem. When you have your cheat sheet that I give you for the test, I'll give you this equation, and I'll give you the R value. Okay, so you don't even have to memorize R. But note, it won't be given to you. It's not usually given in the problem. I mean, I guess it could be, but it usually isn't. All right, so I'm going to have to find delta H of vaporization. Anything else we want to do? Yep.
So is that the Clausius-Clapeyron in a different form?
What?
This whole equation of that?
That is Clausius-Clapeyron, yes.
Oh, it is? Okay.
Yep. Okay, so you guys, what else? I'm going to look up the heat of vaporization in a second. What else do I need to do before I'm ready to kind of plug and chug? What do I need to do?
Convert
Temperature. Do you guys remember what that is? What's the temperature conversion? Kelvin equals Celsius plus?
273.
Yeah, and I'll be honest, I'm not a big, you'll learn quickly, I'm not a big sig fig person, and 273 is good enough for me. If you want to do 0.15, hey, that's cool, but it's not necessary. Okay, so I need to take my 2 temperatures, add 273, and I'm going to go ahead and do that right here real quick. So what's 18 plus 273? That's 291 Kelvin. And 273 plus 32 is 310 Kelvin. Let's get our heat of vaporization and then we'll kind of finish it. Hang on. I'm going to fill this in. 26 kilojoules per mole. Okay, so now let's be a little better with this. Let me list all my, so I have a P1 of 401 millimeters mercury. I have a T1 of 291 Kelvin. I'm looking for P2. My T2 is 310 Kelvin. My delta H, my heat of vaporization, is 26 kilojoules per mole. And my R is 8.314 joules per mole Kelvin. You guys see all that? Yeah, oh, what's wrong? I got lots of chat, Joe. What's wrong? What happened? Did I do something wrong?
T2.
Oh, yeah.
Temperature is 305.
305, yeah, I can't do math in my head. Thanks, sorry guys. You gotta watch my math. It's late at night and I'm trying to do math in my head. Okay, thanks. I figured I heard lots of chatter back there. That's usually, okay. Are we good with everything else? Okay, yeah, you guys just holler at me if I do something wrong. Okay, so that's all my givens. I've converted my 2 temperatures. I've pulled my R value. The heat of vaporization, let's just pretend was given to you because it would be. Anything else I need to do? Here's everything kind of written out. Anything else I need to do before I start plugging and chugging on the equation? There's one thing I still need to do. Convert the kilojoules. So, check it out, guys. Heat of vaporization was kilojoules per mole, R is joules per mole. Now, the secret is it doesn't matter which one you convert, but they need to match. Otherwise, your energy units won't cancel. So, what do we want to do? You said you wanted to convert, which one do you want to convert? Okay, she wants to convert kilojoules to joules. Cool. So 26 kilojoules. This will probably be the one time I show you guys this, and then I'm going to assume you know how to do it. 1 kilojoule is equal to how many joules? Yep, a kilo of anything is equal to 1,000 base units. Right, that's per mole. So my delta H vaporization, my heat of vaporization becomes 26,000 joules. Okay, now, I've got it on the next slide. Everybody's got the notes, but let me show you on the board because I find students struggle with this, doing the math here. So here's what I would do. 26,000. I'm going to plug everything in over here on the right-hand side.
Yes, she said that, like that would be given additional.
What was T1 was 291.
Okay, we should work it out.
T2 was the corrected 305. 291 Kelvin times 305 Kelvin. I'm just putting the numbers in for the variables. Over here I have natural log of 401 mmHg and my one unknown P2. Okay, so all I've done is take the givens that I just wrote on the slide to the equation, just plugged them all in, kind of made sure that my units are going to cancel, you know, the kelvins will they're canceling, and over here, I was given the pressure in millimeters mercury. Is there any reason I can't leave it in millimeters mercury? No? Nothing else has a unit of pressure. I don't have ATM. I'm not doing the 0.0821 liters atmospheres. I'm not using that R value. There's nothing else with a unit of pressure. And the question didn't ask for an answer in any particular unit. If I'm not specific, you guys can pick your favorite unit. I don't care. I would leave it alone because it's one more step to convert it into atmospheres. You can if you want to, though. Nothing wrong with that. But I'm going to leave it alone. There's no reason to change it if I don't need to. Now, what would I do with the math? How do I recommend you do this? Well, this is my basic algebra recommendation. The right-hand side of the equals, I have all the numbers that I need. I would plug all that into my calculator. And let's see what we get. 26,000 divided by, actually, let me do the other side first. 291 minus 3. And then multiplied by 26,000 and divided by 8.314. Okay, and I'm gonna bring it up over here just because I'm running out of space. Actually, these markers are tired for the break. All right, I haven't done anything with the left-hand side. It still looks like this. But I plugged everything in on the right-hand side. Whoops. And on the right-hand side, I don't know, I'll throw a couple of sig figs up here. 0.493, we'll do 3, call it good. On the right-hand side, when you plug all this in your calculator, you should get negative 0.493. So all I did was plug and chug on the right side. Left side's left alone. Okay. I need to get P2 all by itself. In the numerator, all by itself. And I got this pesky thing called the natural log. Can you guys remember, what do I do to get rid of the natural log? Yep. If you forget, there's always a secret way. The secret way is find the ln, the natural log button, on your calculator, and the hint, the secret, is there with it. Always. Unless you have some computer calculator I've never seen in my life before, which is possible. But natural log button on your calculator should have e to the x with it. That's your hint. So, as we just said, you take e to the x of both sides. Now, what does that do? Well, it was exactly what we wanted it to do. It drops off the natural log. So my left-hand side is now just the 401 millimeters mercury over P2. And when I take e to the x of negative 0.493, on the right-hand side, I have 0.611 if I do 3 sig figs. So that step, e to the x, just dropped off, got rid of, whatever you want to think about it, the natural log. So leaves the 401 over P2, equals now e to the x on the right-hand side, converts it to a positive, which is good because I can't have a negative pressure. And so now at this point, gosh, I hope this is really basic algebra. Multiply both sides by P2 and then divide by 401. Let's see, so we get, or divide by 0.611. 401 divided by 0.611. And we get an answer of, not 4, it's 4, is it 401 or 410? No, it's 401, okay. 611. I get a P2 of 656. My unit's still millimeters mercury. I should change it to atmosphere, which is fine. Just make sure you have the right unit, whatever you're. And I go, does that make sense? Well, my temperature increased from 291 to 305. I saw an increase in temperature. I should see an increase in pressure. And I did, from 401 to 656 millimeters mercury. Up. All right, here. Heat of vaporization for this is 26 kilojoules per mole. So I'll come back to this. Okay. All right. Here's your next one. Here's one you guys, it works the same way. You'll see I like to do these in repetition. You're even solving for P2. You guys try this one. I give you the delta H vaporization, the molar heat of vaporization. You don't have to look it up. See if you can follow what I just did with this problem, and then we'll compare answers here in a couple of minutes, and then we'll go on.
Excuse me.
Yep.
For my calculator, how I can use the ELAN just from here.
Let's see. Where's your natural log? So it's, you got to hit second,
Yes.
and then e to the x.
Mm.
So I think for your calculator, you probably have to put in, let's see, 0.49, whoops, I just turned it off. 0.493, make it negative. Second, e to the x. There you go.
Oh, okay.
Okay.
So I gotta put negative first, right?
I don't, for your calculator, you might be able to do, can you do negative? No, you have to do the number and then hit negative.
So I will do these 1.6.
You do 0.493
0.493.
and then make it negative.
Negative.
There you go. And then
I go
second, you want to take e to
second,
the
then
x.
to E to, okay.
Yep.
Thank you.
Yep. Do that a couple times and hopefully you'll have that. Because I'm going to go put my water back. Thank you. All right, you guys, how'd you do? Did you get it? A couple people still writing. I'll give you one more minute, and then we'll go on or answer questions if you get stuck. All right, anybody, any questions? All right, if you're struggling, kind of put it on pause and we'll come back to it maybe at the end. All right. Ooh, that's really bad with glare. Okay, again, just some kind of housekeeping definitions in case you see this somewhere. I'm not going to test you on like the differences here, but boiling point, what we know of as boiling point, you go, what, there's a difference? Well, the boiling point is temperature at which that equilibrium, so rate or speed are the equal of vapor pressure. The liquid is equal to the external pressure. That's when it would boil, when those two pressures become equal. Normal boiling point is the temperature at which it boils when your external is 1 atmosphere. So most of the time, you know, right now we're essentially at 1 atmosphere. Most of the time the boiling point and the normal boiling point are one and the same, but just in case you happen to see it differently, normal is pressure is 1 atm. All right, stuff down here I'm not going to worry about. That was just some heats of vaporization in case you needed them. Again, some definitions here. Critical temperature, temperature above which the gas cannot be made to liquefy, no matter how great the pressure. So again, thinking back to gas laws in Gen Chem 1, you can apply pressure, so much pressure to a gas that you turn it into a liquid. Okay? So critical temperature is the temperature at which you can't do that anymore. Critical pressure, the minimum pressure that has to be applied, that liquefaction I was just talking about. So how much pressure has to be applied for that to happen? This table here, a little more important, so I kind of want to focus a little bit on it, if you can actually see those values. Substances with their formulas or just their element symbols. Idea is, again, looking at those different forces we talked about, you're going to see different pressures, different critical temperatures. So again, just more properties that are affected by our different intermolecular forces. That's really all. Heat of fusion, we talked about heat of vaporization, how much energy it takes to vaporize, so that's liquid to a gas, 1 mole of any substance. The fusion is for going from solid to liquid. How much energy does it take for 1 mole of that substance? And even though we're talking about phase change, for instance, for H2O, there are 2 different phase changes. One is, oops, I set my water back. Solid, they're right next to each other. Liquid, they're a little bit further apart. Gas, there's even more distance between them. So while in name they are different phase changes, melting versus vaporizing, they're also different in terms of where the molecules sit and the energy needed to overcome them. Going from a solid to liquid, you're putting very little distance between them. You're separating them a little bit. But again, it's like military versus you guys versus gases, which are separated all over the place. Tons of energy those kids are exerting. It's crazy. So phase changes are different. You'll see the values are different, whether it's a heat of fusion or heat of vaporization. Okay, so that leaves us with kind of the last part of the chapter here, and that is what's called a heating, or could also be cooling, depending on which way you want to go. Heat up a substance or cool it off. It's called a heating or cooling curve. And I use these, you'll see when we do these problems, these last problems that we have, I use these curves to help me keep count for an accounting of the steps that are happening and that each step requires a certain amount of energy. So in Gen Chem 1, in fact, I'll just write it on here. In Gen Chem 1, you learned this equation. energy, heat energy, how much energy it takes to heat something up, for instance, is equal to mass, so how much you have, times specific heat capacity, which is a constant depending on what the substance is, so you go look that up, times change in temperature, how much you're going to change the substance's temperature. So those three variables come into play in determining how much energy it takes to, for instance, heating or cooling something up. And that's all in Gen Chem 1. That was your only energy equation dealing with changing temperature. Now, we're going to use this here still. However, now you've grown up to Gen Chem 2, and I'm going to tell you the secret we've been talking about all night. Changing phase also requires energy. So of course it requires energy to heat something up, right? To heat up water, everybody should know, requires energy. You put it on the stove, you turn on the stove, and it goes, it heats up. However, changing phase, putting distance between those molecules also requires a certain amount of energy. And so each of the steps along the way requires energy that we have to account for. So, and we're going to see this in a second, this is like worst case scenario. This would be, for example, if I had, let's say, ice at negative 20 degrees Celsius that I wanted to heat up to vapor, let's say at 120 degrees Celsius. So using my little heating curve here, this would be, for instance, my negative 20 degrees Celsius, where it's a solid, it's cold ice. First thing I have to do is bring that up to the freezing point. So my ice cube warms from negative 20 up to the freezing point of 0. And that's step 1. That requires a certain amount of energy. To change something's temperature, boom, requires a certain amount of energy. This would be the equation we use, and we will use, to figure out how much energy it takes to warm up an ice cube, 20 degrees. And then step 2, let me use a different color here, guys. Hang on. So this is step 1. Step 2, I'm staying at 0 degrees, because at 0 degrees, that's when it melts. And there's an energy associated with changing state. Solid to liquid is called heat of fusion. So step 2, I would need the heat of fusion for step 2. Let me do a little thing down here. Again, I like to do lists here. So Q equals mass times specific heat capacity times change in temperature. This would be step number 1. I would use this equation. For step 2, where I'm melting something, I would use heat of fusion, and I'm going to show you all this in just a second. But the heat of fusion is how much energy it takes to melt 1 mole of the substance. All right, back to my steps. So that's kind of what I have to do in my different steps, the first 2 steps. Whoops. Now I'm at, okay, right here, B. At this point I have liquid water at 0 degrees Celsius. I have to keep going because I want to take that water all the way to 120 degrees Celsius. So step 3, I'm going to climb the ladder here between points B and C. Step 3, I'm going to heat up the water, the liquid water, from 0 to, well, water boils at 100 degrees Celsius. So that's where I'm at on my y-axis. So step 3, I'm back to not changing the phase, the physical state as a liquid, but I'm increasing temperature. Anytime we increase temperature, we use our Q equals equation. So steps 1 and 3 will use the same equation. I'll have different values because we have different specific heats for different physical states. But steps 1 and 3 will use the Q equation. Step 2 is going to be a phase change. And then at this point, at the end of step 3, I'm right here at letter C, which is I've got liquid water at 100 degrees Celsius. I have to keep going. I need to get to 120. So right here, Now I'm at 100 degrees with my liquid water. I'm going to vaporize it, change it from a liquid to a gas. That'll be step 4. And there's an energy associated with changing the physical state. This time it's called heat of vaporization. It's a constant. We'll pull that out in just a second. And then finally, I don't want gas, vapor, steam at 100 degrees. My little imaginary problem, I said, take it up to 120. So step 5 would be to take the vapor up to 120 degrees Celsius. That's step 5, and end it wherever it is. Again, that's a change in temperature. I've got steam. I'm heating up from 100 to 120. And anytime I change temperature, that step is going to use the Q equation. So steps 1, warming up my ice cube. Step 3, warming up my water. Step 5, warming up my steam. Those 3 steps involve a change in temperature, and we'll use the Q equals mass times specific heat times delta T. Steps 2 and 4 is where I'm putting the energy in to change the phase. Solid to liquid, then liquid to gas. And they each have their own heat, molar heat of, associated with. It's a constant. You would be given that. And so you'd calculate those energies using those values. All right, so that's kind of an overview. And again, this is worst case. This is if you're taking a cold solid up to a hot gas. And you can do it anywhere in between. It just depends on the individual problems. We'll do some that are easier and some that are, worst case scenario where it's 5. What was it? Way back here with the 5 steps. 3 are going to require temperature changes, so that Q equation, and 2 are phase changes. Okay, here's how I approach these problems. First thing I'm going to do is create that heating curve. And as silly as it seems, when you get your exam back, if you get one of these problems wrong and I don't see that, I'm going to mark there. Where the heck is your heating curve? Okay? I have a PhD in chemistry. I write heating curves. There's no reason, other than being lazy, that you don't do it. Please do it. It helps you with, okay, what steps, how many steps, what do I need to do? I promise you it's in your best interest. Okay, so let's look at this one, and let's talk it through, and we're going to work it out, and then you can do one. So it says calculate the amount of energy needed to heat 346 grams of liquid. Let's circle my givens. Liquid water from 0 to 182 degrees Celsius. And then it says assume that your specific heat of water is this. For the liquid and for the steam, it's this. Okay, so I've got several givens. In fact, it's still missing something too, but hang on. Let's start with, I've got a mass, 346 grams. My initial temperature is 0 degrees Celsius. My final temperature is 182 degrees Celsius. And then it says we have a specific heat of water. It's this guy here. 4.184 joules per gram per degree Celsius. And the specific heat, also called CP or SH, whatever, that's just an abbreviation, of steam is 1.99 joules per gram per degree Celsius. Now, the one thing that this problem didn't give that we need is, of course, we're going to be vaporizing. We're going from a liquid water to a gas. So I also need, I should have given you this, I don't know why it's not on here, the heat of vaporization for H2O for water, and I'm looking it up here. Where is it? It is 40.79. So this is a constant. It really should have just been given to you in that second paragraph. All right, so there's all my givens. Let's do my heating curve so that we can figure out what I need to do, how many steps, all that good stuff. And again, you don't have to draw this to scale. It's really just kind of some side notes so you can remember and know what's happening. So I'm starting here at 0 degrees Celsius. I'll put a little dot here. And it says it's liquid. In fact, I'll write an L for liquid. So at 0, it could be solid or it could be liquid. So it's already liquid. I don't have to convert it. I don't have to melt it, talk about any of that. It's starting in a liquid, and it's going to go up to a gas at 182. So the first thing is I'm going to heat it up to 100 degrees Celsius, where it will boil. It's still a liquid, though, at 100 degrees Celsius. And this is step 1, heating up the water. Step 2 is where I'm going to change it from a liquid to a gas. At 100 degrees, it's going to take some energy to go from liquid to a gas. And then the problem doesn't tell me I can stop at 100 degrees Celsius. No, it wants me to heat that water up even further, the steam at this point, sorry. So the third step, I'm going to take that 100 degrees, obviously it's already hot, but steam, and heat it up even more to 182. So this is one of the not so worst case scenarios. There's only 3 steps we have to calculate the energy for and then add them all up. 3 things that are happening that require energy. 2, changing temperature. 1, changing phase. And again, anytime we change temperature, number 1 and number 3 on my little energy here, I just use the Q equals mass times specific heat capacity times delta T. I've got mass, it was given in the problem, 346. The specific heat for water and for steam are given. They're going to be different. That's why there's 2 different ones given to you. And then delta T, well, how much is it changing? That's going to vary. In step 1, the delta T is, how much is it changing in the first step? 100, from 0 to 100. And what's the delta T for step 2? Or excuse me, step 3 for the other change in temperature? Yep, from 100 to 182, the difference is 82 degrees Celsius. Okay, so my mass, I've got 346. The specific heats, whether it's step 1, where it's liquid water, I'm going to use 4.184. And where it's steam, in step 3, I'm going to use 1.99. And then delta T, we just said, for step 1, it'll be 100. Step 3, it'll be 82. So we'll plug those in and get I call it Q1 for step 1 and Q3 for step 3. And we'll do that in just a second. And then my change in phase, well, that's where the vaporization comes in. In step 2, I'm vaporizing from liquid to a gas my sample. Now, heat of vaporization, 40.79 kilojoules per mole. What does that mean in terms of like writing it out as an equality or as a conversion factor? That means it takes 40.79 kilojoules of energy per every 1 mole of water. Do I have 1 mole? No, it doesn't look like it. I've got a lot more than that. But I'm going to have to convert mass into moles, and then I can use it. Okay, I've got to be in moles. So somewhere, wherever you want to do it, 346 grams, I have to convert from grams into moles. What's the molar mass of water, you guys?
18.
Thank you. 18. So grams on bottom so that it cancels. 346 divided by... I've got 19.2 moles of water. And again, I only want to use moles in step 2. Steps 1 and 3 use mass. So 346 as is good. But then, so for step 2, I'm going to do basically a conversion from 19.2 moles of water into kilojoules of energy using that heat of vaporization. It's just a conversion factor. Okay, so I've kind of all put it all together, what I have to do, what I worked through it, and then you'll just see here's where we go. So Q1, that was step 1, mass, times the specific heat of liquid water, times how much it's changing temperature. I get an energy of about 145 kilojoules. Question asked for it in kilojoules, so I just went ahead and converted from joules into kilojoules right here. Step 2 was that conversion from grams into moles, and then from moles into kilojoules of energy. Changing phase for this guy required 783 kilojoules. And then that was Q2. And then the energy for step 3 is I'm back again to the mass times specific heat times temperature. Mass is still 346. Specific heat is different now because it's a gas, not a liquid. So it was given, though, in the problem, 1.99. And my change in temperature, we already said, was 82. Multiply those together and then convert it into kilojoules. Step 3 takes 56.5 kilojoules of energy. In total, then, you just add them all up. Each step required a different amount of energy. Add them all up, and in total, to do this process, is going to require 985 kilojoules of energy. So the crazy thing is, you guys, in Gen Chem 1, you just learn to use this equation. And you may break it down by solid versus liquid versus gas because you have different specific heats. But you're not adding in, unless you have a really good Gen Chem 1 instructor. Usually they don't teach you about the change in phase part of it. And in fact, if you look at these numbers, the change in phase requires more energy than anything else. So you were really, really off in Gen Chem 1 if you just used that equation. But again, most instructors don't get into intermolecular forces, and because that's really a Gen Chem 2 thing. So this is going to be okay. Here's your problem. We have just a couple problems left. Calculate the heat released. Now we'll talk about that in a second. When 68 grams of steam, so there's my first number, my mass. It starts at 124 degrees Celsius, and it's converted into water, liquid, at 45. And then here are your specific heats. Here is your heat of vaporization. So the constants are still the same as the last question, because it's still water. Now, let's do this. This one's going to be what I call a cooling curve, only because we're cooling it off. Same thing applies, though. It's just that I'm going to start up here at a higher temperature. So I'm starting with a gas at 124, right? You're starting at 124, and I'm going to take it down to 45. Well, it's water, so the first thing is I'm going to cool it to 100. I'm going to cool the gas off. It's still a gas. Cooling it to 100. That's kind of my checkpoint. At 100, I'm going to have a change. So you have to stop at 100 and make your change from a gas to a liquid. So this was step 1, cool it off. Step 2, change it from a gas to a liquid. And then it says it doesn't want liquid at 100 degrees. I want liquid at 45 degrees Celsius. So I'm going to cool it off one more step, step 3, right there. Now, calculations are going to be the same. Anytime you have a change in temperature, you're going to use this guy. Anytime you have a change in phase, this time we're condensing, but it's still the gas to liquid change, you're going to use the heat, the molar heat of vaporization or fusion, depending on what your phase change is. So step number 1 and step number 3 are going to use the Q equals M times specific heat capacity times delta T. And step 2, where I'm changing phase, is going to use my delta heat of vaporization just as a conversion from moles into kilojoules. Yep.
Wait, so is it the same conversion between its liquid and its gas? It takes the same exact amount of energy to raise it into
So, okay, so the difference between vaporizing and condensing, they're opposites. Vaporizing means going from a liquid to a gas, making it a vapor. It's going to require 40.79 kilojoules per mole for water to vaporize water. Condensing, going from a gas to a liquid, it's the opposite process, which means the energy number is the same. It's still 40.79, but it's going to be released. Energy is going to be given off. So you can use the numbers exactly the same way, and you'll just say, at the end, X amount of kilojoules is released. Or if you want to use the negative sign, you can say negative, it's associated with a negative X amount of kilojoules per energy. So the math works the same. The numbers are the same. It's a positive. It's applied if you're heating it up, and it's released or given off if it's cooling. Okay, that was really, really glared bad. Oh, there, that's better. Okay, I think I'm going to prop it up like that. All right, so follow your last steps. It'll work the exact same way, the one I just gave you. Give you a few minutes for that, and I think I got one more for you. And that's better. instance. I never hit record again, sorry. And then we have like two housekeeping slides and that's it. So I'll give you probably 5 or 6 minutes on this at least, and then a couple housekeeping things, and then your guys are out of here. Oops. All right, so if you need some help getting started, I put my heating curve with my steps and kind of what my plan is up on the overhead. All right, looks like the majority are done. I didn't have room to show all my work on here. If you didn't get one of these answers, I broke it down. Again, Q's 1, 3, and 5, the first, the third, and the fifth step. Use the Q equals mass times specific heat times change in temperature equation, and that's where I got these 3 answers. Okay, they were in joules originally because the specific heat was in joules, and then I just divided by 1,000 to get kilojoules. And then steps 2 and 4 is where I was changing the physical state. So I used the delta H, and that's where I got the two different delta H's, excuse me. One is vaporization and one is fusion. So make sure you use the right one. And then I got those two answers. They're in kilojoules because the delta H was in kilojoules, but you had to convert mass into moles to be able to do it. And then when I add it all up, I get around 2,675 kilojoules. Again, give or take, if you rounded somewhere a little different, as long as you're in this ballpark, you didn't get 2,100 or you didn't get 3,100 or something, be in the ballpark, give or take a couple of kilojoules and you're good. Okay, questions on that? Again, if you didn't get something and you want to see my full detail after class, stick around. Oops, got it. All right, just a couple of housekeeping things. Oh, there you go. We're back to you can't see it all. Oh, guys. When this works well, it works really well, but when it doesn't, it goes really bad. Phase diagrams. I'm just going to hold it up. So phase diagrams, these things here, we have them for different substances, just like we have heats of fusion and heats of vaporization. The phase diagram shows you temperature is along the x-axis and pressure is along the y-axis. And you could use this to determine, hey, if I heat up this substance to 150 Celsius, or whatever the units are on the x-axis, what physical state can I expect it to be in? And so you would use this and you'd find your 150 would be way up here, and you'd come up and say, hey, this is the liquid part. It goes in order from left to right, solid, liquid, and then gas. So there's always 3 parts to a phase diagram because there's 3 phases, solid, liquid, gas, and they always go in that order. So you could use it to determine, what physical state you could expect it to be in. Another thing these are used for is, I talked about that applying pressure to get the liquefaction of a gas. So for instance, apply so much pressure to steam, to water vapor, that it becomes liquid water without hitting the right temperatures, that 0 to 100 Celsius. You could apply enough pressure. And you can do that here too. You could figure out, here's pressure on the y-axis. What pressure would I need to be in, at this temperature to get it to be a different physical state? So I have these for all different things. And really it's just, if you can read a graph, if one of these was presented to you, you can read this. It's not, but different substances, they look a little different, just more based on, again, those intermolecular forces. This is for dry ice. So dry ice is a gas at a far greater range because dry ice doesn't have all the forces, for instance, that water does. So at lower temperatures, it's a gas compared to water. And then this one is for, I think this one's actually for water, has some numbers. Oh no, this last one is talking about how if you increase pressure, the melting point and boiling point will actually change. We're going to talk, this leads us into chapter 11, what we're going to do next week. We're going to look at how you can change melting points and boiling points by doing things like making it a mixture and things like that. So